electrical engineering and computer science. I'm really excited and happy and honored to have Markos give this reverse hybrid seminar. So reverse hybrid means it's presented over Zoom, and it's reverse because we actually have people together in the physical world in some of the rooms watching this. And then also let me point out that we have people dialing in from all over the world in different geographies. So let me say hi to everybody, and thank you all for joining. So it's my real pleasure to introduce Markos Papageorgiou, who received his diploma engineer and doctor engineer from the Technical University of Munich in Germany. And he held a variety of visiting and full-time positions all around the world. I will just mention a few, starting with my home country in France, the INRETS, the Institut National de Recherche sur les Transports et leur Sécurité in Paris. He was also visiting professor at the Technical University of Munich in automation, also at the University of at the Technical University of Crete since and then since 2021 he has been a professor also at Ningbo University in China. He's been a visiting professor in a variety of other institutions: Politecnico di Milano, UNPC in France, MIT, Rome, La Sapienza, Tsinghua University. And he's a frequent visitor of UC Berkeley and Go Bears. So he holds a variety of titles. He's a honorary visiting professor at the University of Belgrade, has received a Doctor Honoris Causa from the Aristotle University in Thessaloniki, and a variety of awards as well. He's a lifelong life fellow of the IEEE and fellow of the IFAC. He has served in a variety of high-ranking editor positions. In particular, he was the editor-in-chief of Transplantation Research Part C from 2005 to 2012. And he's the recipient of numerous awards, in particular the 2020 IEEE Transportation Technologies Award, and as a PI of 2 major ERC grants from the European Commission. We're really excited today to find about new results that he has published or will publish on nudging, and maybe a little personal note as well. What I really enjoy when listening to Markos's talk is the ability to, at the same time, anchor the models that he's using in classical traffic theory, but then apply the state-of-the-art control theory and optimization results that we also see in the IEEE CSM community. So a really nice bridge of 2 communities that hopefully we'll hear more today. And Markos, I guess the digital floor is yours.
Thank you very much, Alex. I guess I need to share screen. Can you all see my screen? Can you still hear me?
Yes. Yes.
Very good. So, Alex, thank you very much for the nice introduction. I'm very glad and honored to be presenting the seminar at the University of California at Berkeley, where I have spent several sabbaticals and where I have very good friends and colleagues. Unfortunately, some missing today. That's life. The title of my presentation is Highlights of Lane-Free Automated Vehicle Traffic with Nudging. We all know that human technology has made tremendous advances in many domains, but there is one domain where we could say lags behind, and this is witnessed by traffic congestion that we have daily on virtually all metropolitan areas around the globe. And remarkably, this is in contrast to even simple species like ants that seem to address their transport problems more efficiently. I give here an article. If you read the title, you have the feeling it's about traffic control, but then the last 2 words indicate that it's about ants. In fact, the 2 co-authors are distinguished zoologists who have studied the behavior of ants on their way from a food source to their nest and back. So they built highways, and then they investigated the behavior of the ants and found out that they behave in a way or in a single way that maximizes the throughput on the highway. Something that we cannot tell about urban or interurban areas where human transport takes place. Now, over the decades, there have been several conventional traffic management tools developed, which may mitigate traffic congestion. Our laboratory has contributed in these efforts with several tools. In the last decade, we witnessed also in research a switch towards exploitation of a number of vehicle automation and communication systems that emerge and which can be used also for improved traffic management. And we have also contributed to this area among many other groups globally. So my present seminar is about something that is more in the future, namely the era where CAV, connected automated vehicles, that means vehicles with a high level of automation, will basically prevail. So we have high penetration of such vehicles. So for that period, for that era, which nobody knows when exactly it will come, maybe 1 decade, maybe 2, maybe more, I don't know. Nobody knows. So what I will present today, in any case, concerns that era of CAV. And what I will present is goes under the name TrafficFluid. This is, let's say, a new concept that we suggest, and we are investigating its properties. It is at the same time an ERC Advanced Investigator Grant running from 2019 to 2025. So I have 2 more years to go. And the full title of the ERC grant is Lane-Free Artificial Fluids Environment for Vehicular Traffic. ERC is European Research Council for non-Europeans. TrafficFluid is, a new paradigm that we suggest. You can have this paper here for more details about this concept, which applies again to traffic consisting of CAV almost exclusively. And the paradigm TrafficFluid is based on 2 combined principles. The first principle is that vehicles can drive on the 2-dimensional surface of the road without keeping lanes, without being bound to lanes. The second principle is that vehicles may influence other vehicles in front or aside of them. For example, they may exert a force on them. Like here, you see a fast vehicle, the yellow one, pushing aside some slower vehicles and being able to accelerate and cross. So we call this nudging of front vehicles. Why those 2 principles? Well, let's have a look at human driving. And of course, we all realize that humans as drivers have a very specific perception limitation, namely the fact that they can only look in one direction at a time. And of course, since usually vehicles are driving at high speed, that direction should be the forward direction. And this limitation has at least 2 specific consequences. One consequence is that at some point in time, actually, pretty late in the 1950s, traffic lanes were introduced. I'm talking about parallel traffic lanes because they simplify driving. If you are driving on a traffic lane, then driving reduces to car following, meaning that you just watch and control the distance to the front vehicle. And this, of course, is a simplifying measure, which again was not there before the 1950s because there were much less cars on the road. So even on highways before that decade, you had no lanes. You could drive anywhere on the road surface. Of course, lanes must be wider than the widest circulating vehicles, and therefore the introduction of lanes implies that the lateral occupancy is lower, and this leads to also lower flow and capacity. Another issue is that when you have lanes, then of course you may occasionally need to do some lane changing, and this is known to be an incident-prone maneuver. So there are many there are statistics saying that about 10% of all accidents are due to lane change. A second consequence of the limitation, of the perception limitation, is that since drivers look ahead, their driving is not influenced by what happens behind. That means the entity, driver, vehicle entity, has an anisotropic behavior, a different behavior forward than backward. And that is transferred also to the traffic flow. So we are talking about anisotropic flow, which means, for example, that traffic flow has no pressure like other fluids have. I mean, like water or gas, where particles are pushing particles in front. And this also has some, negative impact on flow, stability of flow, capacity, and so on. So in summary, due to this human limitation, traffic lanes and anisotropy appear, which limits capacity and stability of traffic flow. What about CAV driving? Well, that's pretty much a different thing, because CAV can monitor all around simultaneously, reliably, and fast. And they may even extend their perception area with vehicle-to-vehicle communication or vehicle-to-infrastructure communication. And last not least, they can make fast and efficient decisions because they are algorithmic, they are computer-based. So given these, we can ask the question, is it reasonable that CAV, which are quite different things than human drivers, mimic human driving rules? And the answer that we give with this work and this suggestion is no, at least the working answer. We should maybe rethink about how to organize traffic in the era of CAV. Of course, water particles and gas particles do not have lanes, right? But even in living nature, we have flows that are lane-free. For example, you see here a bird flock, or a fish school. There is no leader, no coordination, no central control. Everything, all the decision making is decentralized. Can I ask whether you still hear me? I'm always a bit uncertain when I'm online.
Very good. Oh, very good.
Okay, because my phone just rang and I thought maybe somebody wants to alarm me. Okay, so we have these examples, and of course they are 100% safe. I've never seen birds falling down because they crashed. And of course they are lane free. Even in human activity, in human society, we see flows that are lane-free, like pedestrian movement or bicycle movement. I will show you here a very short video. That's why I will first explain what we will see. This is a bicycle avenue from Tsinghua University in Beijing that was shot maybe 5 or 6 years ago, maybe a bit different today with electric scooters, but that's how it was at the time. Sorry. And what we will see here, actually, it is an off-peak period. It's not a very peak period. There are two opposite streams, and there is no fixed line in between, no mark in between. So it seems that the share of the two directions depends spontaneously, of course, on the corresponding demands. Also, the desired speeds of the bikes are different. So some people are really in a rush, other people are more relaxed, and so there are a lot of overtakings, but they are not, of course, having any lanes. So that's another example of lane-free driving. You see here the flow out of the camera is much less, the demand is much less than into the camera. So you have seen that the separation limit is not really in the middle, but farther right. And we will see that also in some of our work. Good. So our conclusion is that CAV do not necessarily need traffic lanes and anisotropy, which seem to be fossils from the era of human driving and have to be revisited, whether they should stay there or go. In fact, we expect that driving will be smoother in 2 dimensions, smoother because we will not have abrupt lane changing, which is a very violent, maneuver. We expect higher lateral occupancy and therefore higher capacity. A very important aspect, which might be one of the strongest arguments for introducing lane-free traffic, is the fact that if you increase the road width by some amount, which could be just half meter, 10 centimeters, whatever, then we expect that capacity will increase accordingly, because lane-free driving vehicles will have the tendency to spread and occupy the additional width, and in this way increase the speed and the flow. We all know that particles, in our case vehicles, and their movement essentially determine eventually the characteristics of the emerging fluid. And this is true for water, for gas, for many other fluids. So an appearing research question here is, if we really have the freedom without lanes, without anisotropy, to determine the movement of CAV, what is the movement that would lead to an efficient traffic flow? So with traffic control, particularly with conventional traffic control, our business has been to try to understand the behavior, the dynamics of traffic flow like an external process. And while in this case here, we may be able to actively design the traffic flow, not understand how it behaves, but design it. Of course, subject to constraints, but without the need to satisfy constraints that seem arbitrary in the context of CAV, like anisotropy or or lane restrictions. So in that sense, we may talk about a designed traffic flow or an artificial fluid for traffic. And in our grant, we work in these directions based on 3 axes. The first and most important axis is to design vehicle movement strategies for lane-free 2-dimensional movement. We consider different methodological approaches, different information architectures, different infrastructures, and so on. A second axis is to study, to look at the emergence of macroscopic models from whatever microscopic movement strategy. What is the macroscopic model that emerges, and to try to find ways of an interplay, try to find ways to influence the behavior of the macroscopic model via interventions at the microscopic level. And a third axis is traffic management. That means essentially how can we improve even further safety, efficiency, etc., by rendering some of these things here traffic responsive. That means several parameters or other characteristics of driving, rendering them traffic responsive. So we are glad that we have already several groups in different countries of, who think these things are interesting. And of course, there is a lot of work that can be done along those 3 axes, but also out of them. And we welcome anybody else who thinks that this is something of interest to join this effort. This slide shows some preliminary results that we had at the very start of the project. At that time, we had designed an ad hoc lane-free vehicle movement strategy. We used this strategy for vehicles, for CAVs, to drive on a ring road without on-ramps and off-ramps, just a closed ring road, with a width of 10.2 meters, which corresponds roughly to 3 lanes. And then by simulating the flows, we were able to see what happens at different densities of vehicles within the ring road. In particular, for different densities, we could measure in the simulation the corresponding flow in vehicles per hour. So density is vehicles per kilometer and flow is vehicles per hour. And the result is a flow density relationship, which is usually called the fundamental diagram in traffic engineering. And it has this characteristic inverse U shape. So we see here 4 such diagrams. The green one is without nudging. In the lane-free strategy, we neutralized a term that applies nudging. So you do get capacities that are really high for a 3-lane, like 12,000 vehicles per hour for a 3-lane highway. But, we have this first diagram. The second fundamental diagram results if we increase the nudging. And the third one, the blue one, if we increase it even more to have full nudging, whatever that might mean. So this indicates that nudging indeed increases flow at overcritical densities and capacity. And then there is this fourth and biggest fundamental diagram. What is that? Well, we just increased the width of the roads by 1.7 meters, which is about half lane, to see what happens with the flows. Of course, in conventional traffic, lane-based traffic, if you increase the width by 1.7 meters, you get the same capacity. You don't have any increase because it is useless. But in lane-free traffic, it is very useful. And as you see, it increases the flow and capacity by a corresponding proportion. Good. Let me now come to the second part of the presentation, which is the highlights. I will not be able to go into any depth. I will just mention, drop a few words and show some videos. As I said, we are working on 4 different methodologies for deriving vehicle movement strategies under lane-free traffic with nudging. One of them is optimal control that I will briefly discuss here. A second one is nonlinear feedback control. A third one is reinforcement learning. Unfortunately, I don't have the time. I will not talk about reinforcement learning. And the fourth one is what I mentioned already, ad hoc modeling, which tries to generalize concepts from ACC, adaptive cruise control, to the 2-dimensional case. Okay, so one methodological avenue is optimal control. We may use double integrator or the bicycle model for optimal control. In these first works that I will address, we use a double integrator meaning position, speed, acceleration. But a double integration, because now we have also movement in lateral direction, right? So an optimal control problem is formulated for each vehicle. Excuse me. An optimal control problem is considered for each vehicle independently, and different vehicles may have different sizes, different desired speeds, different constraints, and so on. And then such an optimal control problem is embedded within a model predictive control, MPC scheme, with a look ahead horizon of 8 seconds. And this takes about 12 CPU milliseconds to solve for every vehicle independently. And the replanning for MPC is event-based. Regarding communication, we assume that every vehicle makes its decisions by itself, but each time it makes a decision, it broadcasts the decision to nearby vehicles, so that in an asynchronous way, nearby vehicles may know, with some uncertainty, of course, what other vehicles are going to do. Let's see a first video. This is again a ring road with a width of 10.2 meters. Each vehicle is running the same strategy, although with different desired speeds. So some vehicles are faster, some are slower. The camera of the video follows this specific vehicle, which belongs to those who have rather higher desired speed. So you see vehicles seemingly moving back or forth if they are faster or slower than the vehicle that we are tracking. So this is our vehicle. Sometimes, of course, it encounters stronger, higher densities, and then it has to slow down or to find some way to cross. So again, this is MPC optimal control for each and every vehicle. Now we can do the same thing for an emergency vehicle, just as a case study. This red vehicle here is an emergency vehicle. And at the start of the simulation, this vehicle is like all others, but then it gets a message that it needs to go to a rescue location. And then it has a very high speed, higher than all other vehicles. But the strategy is the same. And there is also in this scenario some cooperation. That means all other vehicles downstream of the emergency vehicle get the message and try to slightly move sidewards to open a corridor for the emergency vehicle, so that it can, as you can see, cross at relatively high speeds. I think it's 40 meters per second in this case. So this is a special scenario with emergency vehicle. Again, all vehicles are moving based on the same strategy. And this is the case where optimal control is being used not for each vehicle individually, but for a whole group of vehicles. So we have one single optimal control problem for a group of vehicles, in this case, 8 vehicles. Within a single optimization problem. This is just one scenario, artificial scenario, where we have 8 vehicles behind each other. And then the last vehicle is the one with the highest desired speed, second highest, third highest, and so on. So if the time horizon is big enough, then the last vehicle will be eventually the first, and the second last will be the second first, and so on. So it's just an artificial scenario to test how does optimal control behave in case of a group of vehicles. For a long time horizon. So what we see is just open loop solution, and it is just the first step towards other investigations that I will mention eventually. So you see here, the fastest vehicle have to overcome all. There are also some obstacles here, 2 standing vehicles and another one that is moving with constant speed. Again, here the optimization is for all vehicles at the same time. And at the end, because of the higher desired speed of the vehicle that was last, it will be the first, second, third, and so on. Why do we do that? Because the next step is to consider on the highway entities. Every entity has its own strategy and is applying its own MPC, but it can be a single vehicle like we had before, or it can be a group of vehicles. For example, a platoon of vehicles which can move like a snake in a lane-free traffic environment, or a flock of vehicles with deformable boundaries, again, which can move. What kind of vehicle should form a flock or a platoon? It's open. It can be vehicles with the same destination or vehicles with the same desired speed or whatever else. So this is still to come. That's just the first step towards it, using optimal control. This is a second avenue, a second methodology, nonlinear feedback control. This is work guided by my colleague Iason Karafilis. There was a physical seminar at San Diego a couple of weeks ago. So this is an excellent piece of work that emerged from this whole endeavor, thanks to mainly to Iason and the whole group. It uses bicycle model in continuous time as a basic model. The resulting control is decentralized, meaning that it is independent for each vehicle. Again, vehicles may have different sizes, desired speeds, and so on. The required information about other vehicles is limited from an area around each vehicle. And in fact, this area can be determined with some consequences, of course, depending on whether it is big or small. For the constraints, barrier functions are used. And what is very remarkable for these developments is that all results produced are rigorous, mathematically rigorous results. So the corresponding works guarantee, for example, no collision, no road departure, converges to nominal values, and so forth. That was, I think, the first paper that we produced. Meanwhile, there is a paper that is just submitted but available in archive, in which a lot of tremendous generalizations have been introduced. And we can see here also a simulation using this control, decentralized control for each vehicle. What we see here is a highway. We will see the camera will be moving this time, and we will see some vehicles exiting, some pre-specified to exit vehicles exit. And you see here this line, this orange line, it is essentially the corridor it is the road boundary, the left road boundary for the vehicles who want to exit, while all other vehicles have a full road as a boundary. So as said, different desired speeds. Some vehicles exit, should be in different color, but they are not. So you see they exited already. The others continue. Now artificially we let them enter. Again, just to demonstrate that this can be done, of course, collision free, but also relatively smoothly and swiftly. Is there any infrastructure that requires, even for conventional traffic, lane-free driving? Alex, your city, your country.
Yeah, if you can drive through this, I think you can drive anywhere in the world.
So this is the Arc de Triomphe in Paris that many of you probably know. This is the roundabout. This is the Arc de Triomphe. This is the famous Avenue des Champs-Élysées. And this is the roundabout around it. And it features a width of 38 meters. So this width here is 38 meters, something like 12 lanes. And to make it worse, there are 12 radial streets. If you count them, they are 12 bidirectional radial streets. So that means you have a total of 144 different origin destinations. So drivers will have to find their way. I have driven many times in this roundabout. Of course, there are no lanes, no markings of lanes, and it wouldn't be possible to have lanes here. And Luc Julia, who is considered an icon in artificial intelligence and autonomous driving, he had a keynote in 2021 where he mentioned that, in his opinion, there are two main reasons why completely driverless vehicles may never be able to drive, may never appear on the roads. And the one of the two reasons that he mentioned, the other is also funny, but this is the one that we are interested in, is that autonomous or driverless vehicles would never be able to drive on this roundabout, on this specific roundabout. So that was, of course, a trigger for us, since we were working already in lane free, to take the chance and try to do it. And I will just have a video here in simulation where we have a feedback strategy, slightly modified for a ring road that is applied. And you see here different vehicle, different colors. Every color is a different destination. So the blue ones go to Avenue des Champs-Élysées. And you can see that as a case study, we managed to overcome this problem, at least in simulation. Okay, if we move one step further, we may ask the question, what kind of macroscopic models could we have in case of lane-free traffic with nudging? And here there is a very, very significant stream of work, again, by Iason Karafilis, who tries mathematically to establish the ties between microscopic movement and macroscopic flow. But I will concentrate here on a more empirical avenue of work that we are having, where, for example, for this highway with 10 sections, each one 500 meters long, an off-ramp and an on-ramp, we may simulate vehicles driving lane free with nudging, and with demands that trigger a congestion here at the on-ramp, which may spill back. So we can create a microscopic simulation of that. You see here the visualization. So we have here 1 hour of simulation on the x-axis, and on the y-axis we have the 10 sections. And in the heat diagram, you see here red is congestion that is created at the merge section and is spilling back. So if we take a conventional macroscopic model like CTM, cell transmission model, product of Berkeley by Carlos D'Aganzo, extended in the sense that there is an extension in what we use to be able to also model capacity drop. Anyhow, if we calibrate the parameters of this model using data from microscopic lane-free situation with nudging, then, as you see, we can reproduce reasonably well the microscopic simulation results. Of course, we are doing it also with other models, more complex, different than conventional, and so on. But what I would like to say here is that if we investigate the impact of the road width, so the nominal road width is 10.2 like before, but we may reduce it or increase it by quarter lanes, by 85 centimeters, and recalibrate CTM and try to see what is the value of the capacity parameter of CTM for lower widths or higher widths. Well, what we get is an exact line, or almost exact line, an exact proportional behavior between width of the road and capacity. So every of these curves, every of these lines indicates that we have a proportional increase of capacity as a function of the road width, even if it is incremental. And the different lines are because we have different nudging. So this is for no nudging, partly nudging, and full nudging. So nudging also increases capacity, but the width of the road also increases capacity. And the same thing can be done for the critical density. Maybe it is less important for this endeavor. And this is a basis, although we work the other way around, we assumed that this happens, but this is the basis for a control measure, traffic control measure called internal boundary control, IBC. What is it? Well, consider a road or a highway or an arterial with a total width W. Total width meaning that we have two directions, direction A, direction B, and the total width applies to the whole road for both directions. Now, usually, conventionally, we will have, of course, an internal boundary that is exactly in the middle and it is a straight line and doesn't move. But the idea of IBC is to have as an internal boundary a space function which is even changing in real time. So we introduce as a control input what we call sharing factors. And this is a function of time. In discrete time, we may change the sharing factor to better accommodate the traffic conditions and the demands in real time. So to get an idea of what I'm talking about, let's take again an example. This is a highway with 6 sections, 500 meters each. There is an off-ramp, on-ramp. This is one direction, direction A. This is the other direction, direction B. Again, with on-ramp and off-ramp. And this is the no control case, meaning that the separation, the internal boundary is fixed. While here we have control. That means we have a controller. In fact, it is a linear quadratic regulator that controls the internal boundary of every section independently. So every section has an internal boundary that may move upward or downward according to the linear quadratic regulator and according to the traffic conditions, of course. So for this case, we apply, for better demonstration, this kind of demand. So over 1 hour of time, we apply at the upstream, at the beginning of direction A, we apply this demand, a surge of demand, and then a reduction, and then shifted in time, the same thing for direction B, while the on-ramp demands are constant. So that's the idea, and we may now see what happens. At the beginning, direction A gets the higher demand. You see in the control case, the internal boundaries are shifting to accommodate the increasing traffic. Here in no control case, congestion appears at the merge and spills back, while congestion here is completely avoided. And eventually we will have a stronger inflow in direction B. You see already the boundary moving downwards in the control case. And in the no control case, again, we have a congestion in the merge section that spills back, while in the no control case, it is again avoided. So this is internal boundary control. I believe that there are so many roads, arterials, highways, freeways all around the world that could hugely profit from something like that. Of course, there are cases where you may have very strong flow simultaneously in both directions. There, the benefit may be less. But this is very flexible because you may even increase capacity around on-ramps, not along the whole direction and the whole highway, but only around on-ramps wherever you need it. So I believe there is a lot of potential for this measure. And this simulation that we have seen was based on macroscopic modeling, but meanwhile we have it also verified microscopically. So you see the same highways before, just a part of it. This is an on-ramp, for example, and this is an off-ramp, the start of an off-ramp. And you see the two directions and the two internal boundaries. The red is for the upper, for direction B, and the green is for direction A. And you see already that it has shifted because of the higher demand, the higher density. In direction A, it has shifted upwards, and eventually at some point it will shift in other direction. Of course, every time there is a shift, there is a time delaying applying. That means the shift is applied first to the restricted direction so that vehicles can drive out of that zone. And with only a time delay, it is applied also to the widened direction. That's why you see sometimes these two lines being away from each other. So this is IBC. And I have a last highlight, which is again a first step. We are currently working on developing the further steps. It is joint optimization, again, optimal control of all vehicles simultaneously, but now for an urban junction without signals and without lanes. So you see vehicles are arriving lane free. This is not so important. The most important is that they are allowed to cross signal free as they come and lane free. And every one of these approaches has three movements: straight, left, right. So somebody will have to take care that they don't crash on one hand and that they go efficiently through the intersection. And this somebody is the optimal control problem, which as a first step considers all of them. And what I will show you is just open loop, but we are in the process of framing it within model predictive control and go further steps. So here is what happens. Again, a single optimal control problem takes care of everybody and results in these. We can see it a second time. So that's the last highlights. And if you are interested in having more information, also looking at publications and so on, this is the website of the project. Thank you very much.
Thank you, Markos. So we have a few minutes for questions. I know for the people in the physical world, you might have to go to the next room at the end of the hour. For those online, I think if those have flexibility to stay, I can definitely stay as well. Thank you, Markos, for this is very inspiring talk. Thank you for thinking futuristically, not just today's problem, but tomorrow's problem. And also, of course, thank you for choosing my hometown for your first case study. I'll have the privilege of the first question and then pass it, but this is really an open question and I'm not expecting a mathematical answer, but I'm really curious. You showed the funnel diagrams, how they change with this new paradigm. Then you showed the discretized macroscopic models like CTMs with that paradigm. So my natural question would be, if there is ever a PDE to model this in a fully continuous world, do you believe that the approach you show would lead to non-anthropic shocks? And if so, maybe are there new forms of instabilities that could arise from it? And I know this is a very open question. I'm just asking about what you think.
There is a lot of work. I mean, a lot. There are a couple of articles that have been published, again, under the guidance of Iason Karafilis, and who derived PDEs formally based on a specific two-dimensional cruise controller. And these PDEs, of course, have specific characteristics, and we are in the process of investigating them. And there is a possibility to go directly from micro changes, either of functions or of parameter values, to the macro model. Of course, we do need some also there some calibration or validation exercises, because the passage from micro to macro is taking place assuming that there is just one dimension of flow, not two dimensions of flow. So we need some verification of that. But I think that nevertheless, the derived macroscopic PDE are accurate, should be accurate enough to describe what happens. So what I showed here was an empirical approach where you take a ready model, discrete time, and try to see what is the best match, good enough, and good for some purposes. But we also have the second approach that I didn't present here, where we go directly from the microscopic movement strategy to the macroscopic PDs.
Thank you. We can take questions from the audience. It looks like Murat, you're about to speak.
For me, so question is about the boundary control. So would the infrastructure be disseminating that information, making the decision and disseminating this information about where the boundary is?
Yes, if I properly understand the question, there would be an infrastructure-based controller that essentially runs the linear quadratic regulator. The information needed is density on each section of each highway, something that we even have with conventional traffic. And based on that, it would specify the curve, the space-dependent curve, which is the internal boundary, and communicate it to vehicles that enter a section, they should know what is the internal boundary, or what is the curve of the internal boundary, because we are considering it in a space discrete way, as I show it in the first video. But when we run the microscopic simulation, we translate it into a continuous, into a smooth space-dependent curve, and this is communicated to the vehicles.
Thank you.
Is there any other question from the audience in the Newton room or online? I'll ask one more if there's none. I'm curious, Markos, to support this vision, how would the current car sensing infrastructure would the current car sensing infrastructure need to change? Obviously, the control paradigm needs to change, but do you need to even change the sensing?
I believe that most of the sensing would be the same. I don't see any reason why it should change. You need information from all around. Maybe in current plans of sensors, the rear part of the vehicle is a bit underrepresented, and this might have to change. So I took this from the internet. Of course, you see the front part is longer of the sensed area than the rear part. This might have to be improved, but essentially I don't see any need for special developments either for the vehicle or for the infrastructure compared to CAV that are lane based and have no nudging.
Thank you. Looks like Michael has his hand up. Michael, you're calling from Davis, right?
Yeah. Well, thanks.
Hi, Michael.
For hi, wonderful talk, and thanks, Alex, for sharing this with the broader community for this exciting seminar. So, Markos, I saw your initial simulation results with the capacity, and I estimated it's roughly, if you convert to lanes, like 5,000 vehicles per lane. That's a lot more than the regular lane capacity. Normally we're targeting at 2,400. So I was wondering what's in the model parameters. Like, you're assuming a much shorter response time or reaction time, or
Michael, you should consider this is a ring road without on-ramps and off-ramps. So there is no need for lateral movement other than for overtaking. So this is a very high flow, of course. We could have even higher either way. But it's unobstructed by lateral movements due to on-ramp and off-ramps. And so this is one part of the explanation. But yes, lane-free means that on those 3 lanes, occasionally you can see even 5 vehicles, because we allow, and actually we wish at high densities, to see vehicles driving exactly on the boundary, because then you can exploit best the whole width of the road if you have vehicles on the boundary, but without exceeding them, of course. And we have good ways for doing this. So you have already 2 vehicles at the boundaries, and then sometimes you see even 3 vehicles temporarily in between. So it's a multiple of what you get in lane-based traffic. And also, if you don't have lanes, sometimes it is less risky if a vehicle is in between of 2 vehicles in front. You can have closer distances at less risks. So I believe that all of that is leading to these high values. But I must say that several colleagues or collaborators wanted us to test different, concepts like lane-based, ACC, etc. It all depends upon after all, how much lateral movement you will need to have. Because if you put vehicles like in California Path 20 years ago with CACC at 5 meters from each other on lanes, you may reach these and even higher flows. But it will be very difficult then to have lateral movement and so on. So what I would say is, yes, you can reach high flows, very high flows, thanks to lane free. This is something additional compared to lane based, but the behavior, the final behavior and capacity should also take into account what happens when you have on ramps and off ramps. And we have seen several videos with on ramps and off ramps, which are very promising in the sense that, you know, when you have lane based traffic, there are hundreds of papers. Even we have produced a few years ago such a paper for automated merging of vehicles. You need special, you know, special controllers for vehicles to merge from an on-ramp onto a single lane. You need to open a gap and so on. You need to have communication, cooperation, and so on. In lane-free traffic, it is much smoother. We never felt the need to do something special for the merging. We just do the
That's a
same
very
like,
good point.
yeah.
Yeah. Thank you, Markos.
Hi, Professor. I have a question. So in this talk, you presented some results about nudging, and you have mentioned the terms like complete nudging and weak nudging, or something like that. So how do you quantify a nudging effect, and have you also studied the setting where this nudging can be not homogeneous? In the sense that some vehicles can be aggressive in terms of their nudging and others may not be.
For example, we have an aggressive nudging, a stronger nudging in the case of the emergency vehicle. The emergency vehicle itself has a stronger nudging to be able to, you know, to open its way. Other than that, we may have different nudging levels for different simulations just to study the effect, but we don't consider that different vehicles will have different nudging levels. And by the way, please take into account, I say vehicles behind nudge vehicles in front, but in reality, there is no physical pushing like in water or in other fluids. The point is that my vehicle senses the vehicle behind and applies, my vehicle applies to itself the nudging force. It's not the vehicle behind that pushes me. It's its presence that makes my controller apply a pushing force. So sometimes this is overlooked. So it's not in the hands of somebody to say, now today I feel like aggressive, I will increase my nudging. It's, you know, it's the influenced vehicle that applies the nudging.
We have one more question online from Hashmatullah.
Yeah, thank you very much. Thanks for the great seminar. Basically, I have two questions. First, assuming that in the near future, of course, we will have AVs and maybe CVs as well if we have the infrastructure. But what if we have both CEVs and also connected vehicles where human driven, I mean that it's driven by a human being, but still they communicate with other vehicles and also with the infrastructure. Will this model be applicable if we have both CEVs and also CVs? My second question would be, you showed us like the implication in an intersection where it was kind of signal free. Is there any kind of research where pedestrians and also cyclists are included in the optimization process? So we don't have only vehicles, but also we have other users in the road. Thank you very much.
Very good questions. Regarding the first one, we do plan to, at some point, also consider situations where we will have manually driven vehicles. And we did not yet decide how to handle them. Of course, it would be necessary for the automated vehicles to know which ones are manually driven vehicles, so that they apply a special, strategy around them. We don't know whether it would be good to have the manually driven vehicles on a lane on the right-hand side of the road or on the left-hand side of the road, or just as free agents anywhere. We don't know if it will be possible to avoid conflicts with manually driven vehicles, whatever they do, probably not. So we will need to take into account some special conditions for these special vehicles. In short, we are thinking about it. It is in our plan to consider it, but we didn't yet touch it, and we don't have yet concrete ideas. If you have, we would be happy to get informed. Now, regarding the junctions, that's also a very good question. Indeed, so far and in our short-term plans, we don't consider pedestrians, but there are other groups. For example, Technical University of Munich, Professor Klaus Bogenberger group, are also working on lane-free traffic, and even more than us in the urban environment, and they are also developing such signal-free controllers in which they are incorporating or intending to incorporate cyclists and pedestrians. And by the way, I'm mentioning Klaus because we have quite a close cooperation. They have also a physical simulator, for that you can engage for lane-free traffic, so that you get a quite nice view of what is happening around you and feel it better, and also some small robot cars that may be used to simulate some of these cases or others in an even more realistic environment.
Thank you very much.
Good. Do we have any other questions? Okay. Well, let me thank you again, Markos, for giving this wonderful talk. This was really exciting. This talk is being recorded, so we will post it, I assume, as a minimum on the ITS website, and we will make sure that the link is distributed to all the participants. Thank you, everybody, for coming. And with this, Chinmay, if you can stop the recording, and then we'll close the session.